So in this lesson we're going to work on how to solve exponential equations. Now we should have solved exponential equations in prior units. For instance, we had kind of some basic ones like 2 to the x equals 8. And the way we solved those is we were able to rewrite and get a common base. So we had 2 to the x equal 8 could be written as 2 to the third. So therefore x had to equal 3. And that was a pretty basic one. So the idea we were simply trying to find is what is the exponent that you put on 3 to get 8. Right? So we're going to do some tougher ones that we can't really do, we can't get to be the same base. And so we're going to kind of show you how to solve those using logarithms. So we're going to start off with our first example. We're going to have 2 to the x equals 10. Okay, so the problem here is I cannot get a common base between 2 and 10. Okay? So what I'm really looking for is I'm looking for what's the exponent I put on 2 to get 10. Okay? Well, similar to, solving a square root or a squared problem, the idea is to use an inverse. Okay? And the inverse to an exponential is a logarithm of the same base. Okay? So what I'm going to do is I'm going to take the logarithm of both sides, and I'm going to do it of base 2. So log base 2 of 2 to the x equals, and I'm going to, whatever I do to one side I have to do to the other, log base 2 of 10. Now the idea of that is that log base 2, this piece, and 2 as a base of an exponential are actually inverse functions. They actually, in essence, cancel each other out. So log base 2 of 2 to the x is simply x. You should have seen that in kind of a different video that we did. So that means x is equal to log base 2 of 10, which should make sense from some of the things that we talked about in prior videos, is that log base 2 of 10 means the exponent you put on 2 to get 10, which is what we're trying to find in this problem. Now, how do I get this answer? Well, I apply that change of base property that we learned. That is the log of 10 divided by the log of 2. And just punch it right into my calculator and get my decimal approximation. So that's going to be log 10. Make sure you close that parenthesis after the 10. Divided by log 2, that is 3.32. Now this is not an exact answer, it's an approximation. Okay, so if I could check my answer, 2 to the 3.32 is about 10, which makes sense because 2 to the third is 8 and 2 to the fourth is 16, so 3.32 makes sense. So we're going to look at a second example. So let's look at 3 to the x plus 4 equals 8. So here, again, we're going to solve for x. So first thing we want to do is we want to get rid of the 4. So we want to isolate the base to the exponent. So we want to isolate the 3 to the x. So we get 3 to the x equals 4. Now what we want to do is we want to take the inverse of an exponential of base 3, which is a log base 3. So I'm going to take log base 3 of both sides. So log base 3 of 3 to the x equals log base 3 of 4. Again, the log base 3 and then base 3 to the x cancel each other out. So I'm left with x equals log base 3 of 4, and then apply that change of base. So this is log 4 divided by log 3, and again punch that into your calculator. Log 4 divided by log 3 is 1.26, so x equals 1.26. Alright, let's do one more example. let's do 4 times 2 to the x minus 1 minus 3 equals 8. Alright, so 4 times 2 to the x minus 1 minus 3 equals 8. So again, we want to isolate, we want to get this 2 to the x minus 1 by itself. So we're going to get rid of addition and subtraction first, then multiplication and division. So we're going to add 3. So I get 4 times 2 to the x minus 1 equals 11. Divide by 4. So I get 2 to the x minus 1 equals 4 goes into 11 twice. So it's 2.75. And then we are ready to take log base 2 of both sides. So I'm going to take log base 2 of 2 to the x minus 1 equals log base 2 of 2.75. Now here, instead of being left with x, I'm going to be left with x minus 1. So I get x minus 1 equals, and I'm going to again use that change of base. I'm going to take the log of 2.75 divided by log of 2. And again, use the calculator. Log 2.75 divided by log 2. 1.46. So I get x minus 1 equals 1.46. And then to solve for x, one more step, so x equals 2.46. And there we go. So that's how we solve an exponential that requires a logarithm to do it. Okay? I'm going to do one final example, kind of show you a different way to do this problem, or a different way to do a problem that you might choose differently. There's kind of multiple ways to solve these problems, so let's just do one last one a different way. So let's do example 4. So let's do 5 to the x equals 12. Alright, so a different way to do this problem is to actually use properties of logs. Okay? So what I'm going to do is I'm going to actually just take the log of both sides. Instead of base 5, I'm going to take just log base 10, or the common logarithm of both sides. You'll see how this works out similar anyway. So if you remember, one of our properties of logs allows us to pull the exponent down in front. So this becomes x times the log of 5 equals the log of 12. And then to solve for x, we divide by log 5. And notice you get this log 12 divided by log 5, which really looks like the change of base, which is exactly what we would have had if we would have taken log base 5 of both sides. So x equals log 12 divided by log 5. So x equals 1.54. So I can really, the idea here is I can really take the log of any base of both sides. Log base 5 of both sides makes a lot of sense because it's the inverse of an exponential base 5. Those cancel out, leaving you with the x. But you could also take the common log of both sides. Allows you to pull that x down in front using one of our properties of logs. And then you don't actually have to apply the change of base that already is kind of done for you in that problem. Okay? So this is just a second way. There's other ways too. So again, if you need some extra help, find your teacher and ask. We can kind of show you there's another third way as well. We could probably teach you how to solve them as well.